Every secure digital ecosystem relies on strict exclusion zones. These databases hold raw, unpublished information that must remain permanently sealed from the public web. To guarantee those boundaries hold, software teams spend hundreds of hours building specific components whose explicit purpose is to be completely ignored by live systems. This text interface displays a primary forensic artifact of that engineering paradox. The metadata reads, Scheme Title, Draft Placeholder Scheme. It is part of the Draft Exclusion Registry Protocol. Within the software architecture, this file contains no actual product data. It is an empty, hard-coded shell designed to mimic the exact structure of an internal working draft. The source notes attached to this placeholder define a critical operating boundary. They dictate that the pipeline must verify this specific draft scheme is, quoting the text, never exposed to the public registry or sitemap. By setting that strict rule, this artifact becomes a specialized tool for negative testing and data boundary verification within a continuous integration and deployment pipeline. A standard test confirms that a system successfully completes an expected action. A negative test reverses that logic. It actively hunts for the presence of a specific failure to ensure the system rejects invalid states. The stakes for this specific rejection are high. If an internal draft slips past the database filters and leaks into a public sitemap, search engines instantly crawl and index proprietary data for the entire internet to see. To understand how modern networks prevent those leaks, we will reverse engineer this specific placeholder file and examine how systems mathematically guarantee their data boundaries. Structural security relies on the engineering of specialized dummy assets that continuously scan for microscopic fractures in the system's logic. Before a software build goes live, a sitemap generator systematically maps out all available public data. This state machine diagram illustrates a standard dual-state database. Nodes A and B are published, while node C is a draft. To build the registry, the generator queries the database, extracting nodes A and B, cleanly ignoring the draft. That query logic relies on a simple filter, often a line of code like where status equals published. This creates a fragile dependency, because the filter only works if the underlying database schema remains exactly the same. If a developer introduces a subtle schema migration, the data structure shifts and the established query pathway glitches. Mechanically, Node C bypasses the broken constraint, writing itself straight into the public sitemap output. For system architects, this is a severe vulnerability. A leak here violates data compliance and exposes internal company strategies before they are ready. Standard monitoring logs rarely catch this leak. As far as the system is concerned, the generator asked for data and the database provided it. No error codes are thrown. Because the code cannot identify its own failure, architects cannot rely on it to protect the boundary. The final sitemap output itself must be continually verified. Static query filters fail silently when structures change, demanding a highly aggressive verification model. To prevent these silent failures, engineering teams run automated test suites during every deployment to check the logic before it hits production. The initial instinct is often to test the sitemap query by running it against the actual live drafts sitting in the database. This diagram compares the environments. Production data is highly volatile, with users constantly creating and deleting drafts. When automated tests point at these live variables, results become erratic, passing 1 minute and failing the next. These are known as flaky tests. When developers see tests failing randomly for reasons unrelated to the code, they start ignoring the warnings, rendering the suite useless. To solve this, engineers remove live data from the equation entirely, creating a mock object known as a test fixture. Instead of querying live data, the hard-coded placeholder file is forcefully injected into the empty test environment, locking firmly into place as an immutable baseline. By hard-coding the placeholder, the system establishes strict mathematical determinism. The test suite now knows the exact parameters of the draft object every single time. Reliable verification requires stripping away the chaos of human-generated data. By utilizing engineered, immutable constants, tests only evaluate the integrity of the code itself. With the static placeholder pinned, the pipeline enters active execution. The suite executes a negative test, asserting what must not exist. The automated pipeline script commands the sitemap generator to process the isolated test environment containing our pinned placeholder. Once generated, the pipeline evaluates the output using a critical logical assertion, shown here. The logic commands the system to scan the output document, searching for the banned string, ensuring the result equals false. The system confirms the file's absence. The assertion evaluates to true, and the pipeline illuminates green. Passing this negative test acts as an automated clearance. The new code is verified as safe and immediately pushed forward to the production release. But if a bug compromises the query logic, the placeholder bypasses the filter into the sitemap. The test scans, finds the banned string, the assertion evaluates to false, and the pipeline violently breaks in red. That failure acts as a systemic emergency brake. It instantly halts the entire deployment, freezing the code in place before the vulnerability can reach production. By implementing a negative test assertion, developers force the system to check its own work. It turns a silent, invisible data leak into a loud, unavoidable build failure. Moving past the isolated unit test, we can see how this exact logic scales up to protect the macro architecture of a live enterprise software system. This map displays the overarching defensive structure. The deployment pipeline acts as a massive fortified wall between the internal database and public registry. The Draft Placeholder Scheme serves as a verification trigger, identifying vulnerabilities in this wall before any new data push is authorized. The Draft Exclusion Registry Protocol functions as an architectural poison pill. It is carefully placed inside the system, designed to trigger an immediate automated shutdown the second it is ingested by public-facing code. Robust data boundaries cannot rely on static query filters, assumptions about database structures, or hoping users format correctly. Continuous, automated verification against fixed constants provides the only acceptable mathematical guarantee that those boundaries remain intact. This resolves the initial paradox of why engineers spend significant resources writing code that has no place in the final product. They engineer these assets to act like trackers inside a circulatory system. The placeholders hunt for systemic vulnerabilities and expose fatal leaks in the logic. High-integrity systems depend on the intentional design of negative assets. The strength of the architecture is measured by its ability to identify and reject its own invalid states. The exact files explicitly designed to never be exposed are the foundational pillars keeping the entire architecture secure.